In 1944, Nazi Germany was losing on every front, yet behind the lines, engineers unveiled weapons so advanced they seemed like science fiction. Jet fighters that outpaced any Allied plane, rockets that rained destruction on London, even rumors of bombers targeting New York. Hitler's secret science weapon inventions were real, and some experts believe they could have changed the fate of the entire war. But how close did Germany come to flipping history? And what stopped their wonder weapons from deciding the outcome? The answer begins with the arsenal on the edge, and a single decision that could have altered everything. The arsenal of Nazi Germany's secret weapons sprawled across a spectrum of ambition, from the practical to the fantastic. At its core stood the V-1 flying bomb, a pulsed jet-powered cruise missile that buzzed over the Channel, unleashing a new kind of terror on London. Alongside it, the V-2 rocket broke the boundaries of warfare, becoming the world's first ballistic missile, striking without warning, faster than any defense could react. These were not isolated projects, but part of a broader push to leapfrog Allied technology through radical design. Jet propulsion emerged as the centerpiece of this effort. The Messerschmitt Me-262, the first operational jet fighter, could outrun any Allied plane and climb higher, powered by twin Jumo 004 turbojets. Its sibling, the Arado R-234, became the world's first jet bomber, designed for speed and survivability. Both aircraft reflected a shift toward speed and altitude as shields against interception, a philosophy that echoed through the Luftwaffe's late war projects. Beyond the front lines of production, German engineers drafted blueprints for weapons that seemed to belong to another era. The America bomber, a multi-engine giant, was conceived to cross the Atlantic and strike the United States. Even more audacious, the Silber-Vogel skip-glide bomber promised suborbital flight, skimming the edge of space to deliver its payload. Flying wing prototypes like the Horten Ho 229 hinted at early stealth, while rocket-powered interceptors and rumors of death rays fueled the mythology of the Reich's scientific edge. Each project reflected a different answer to the same question. Could technology alone reverse defeat? From pulse jets to ballistic missiles, jet engines to radical airframes, the Wunderwaffe family embodied both the promise and the peril of betting everything on invention. By the summer of 1943, the German war machine was running on fumes. The Allied bombing campaign, relentless and methodical, hammered synthetic fuel plants at Leuna, Hoylitz, and Scholven. Each raid carved deeper into the Reich's reserves. In January, Germany's synthetic fuel output hovered near 175,000 tons a month, with about a third earmarked for the Luftwaffe. By October, bomb damage and disrupted supply lines had slashed total production to less than 90,000 tons. Aviation fuel allocations for flying units fell to a crisis point, sometimes below 30,000 tons a month, while the Luftwaffe's operational needs dwarfed what was actually available. Shortages rippled through every level of the Air Force. Training schools, once able to graduate over 1,000 new pilots each month, saw numbers collapse. By December, fewer than 250 fighter pilots completed the program, many with only a fraction of the flight hours previously required. The Luftwaffe needed 4 times that number just to match losses at the front. Factories tried to keep pace, dispersing production underground and improvising with lower-grade alloys, but the flow of finished engines and airframes slowed under the pressure of constant raids. Maintenance crews struggled to keep aircraft flying as spare parts and fuel dried up. The strain was visible in every operational report. Planes grounded for lack of kerosene, squadrons flying half-empty, and pilots sent into combat with barely enough hours behind the stick. These constraints forced German leadership to confront a hard truth. Without fuel, pilots, or reliable production lines, even the most advanced designs were little more than blueprints. The war's outcome would hinge not just on invention, but on the ability to sustain and deploy what was already on the drawing board. Inside the Reich's war rooms in late 1943, a single question dominated every strategy session. With resources vanishing and the skies filling with enemy bombers, where should the last reserves be thrown? Archival records from Luftwaffe High Command and Speer's armaments conferences reveal a moment when a different path was on the table. Instead of chasing dreams of retaliation through new bombers or miracle attacks, some staffers argued for a total pivot. Defense first, everything else second. The proposal was stark: halt all offensive Wunderwaffe projects that couldn't be fielded within months. Pour every available drop of fuel, every spare engine, and every trained pilot into jet interceptors and radar-guided air defense. Surface-to-air missile programs like Wasserfall and Typhoon, though still experimental, would get priority testing slots and fast-tracked resources. Radar networks would expand, not just to spot bombers, but to direct massed intercepts day and night. The minutes from these debates, preserved in the Bundesarchiv, show a rare moment of consensus among technocrats. If the Reich could not regain the skies, nothing else mattered. This was not just a technical shift, but a doctrinal one. The Luftwaffe's scattered fighter wings would be reorganized into concentrated defensive belts around vital targets. The Ruhr, Berlin, and the oil plants still left standing. Production lines would focus on the Me-262 as a pure interceptor, abandoning the costly conversion to a bomber role. Training programs, already gutted by fuel shortages, would allocate their last reserves to pilots capable of flying jets and advanced rocket fighters. The gamble was absolute. Make the skies over Germany so lethal that Allied bombers would pay an unsustainable price for every raid. If this policy held, the outcome of the air war and the fate of the invasion waiting across the Channel could look very different. The promise of the Me-262 as a war-changing interceptor ran headlong into the mathematics of production and attrition. By the end of the war, German factories had completed around 1,300 Me-262 airframes, yet fewer than 300 ever became fully operational. The bottleneck was the Jumo 004 engine, a technical marvel, but one that rarely survived more than 25 hours of flight before requiring replacement. Each sortie burned through precious synthetic kerosene, straining a fuel supply already cut to a fraction of what the Luftwaffe needed. To field a force of 1,000 jets, as some planners dreamed, would have meant producing not just airframes, but thousands of replacement engines every month. Maintenance cycles were relentless. Engines built with low-grade alloys, forced by nickel and chromium shortages, wore out far faster than design specs promised. Even at the peak of underground production, sites like WWII and Berg, engine output lagged behind demand, and spare parts were always in short supply. Pilot training faced its own crisis. The compressed syllabus meant jet pilots entered combat with minimal hours in the cockpit, often skipping advanced emergency procedures entirely. Attrition from accidents and operational losses mounted, with Galland himself warning that the Luftwaffe was burning through both men and machines faster than they could be replaced. At any given time, only a fraction of delivered jets were mission-ready. The numbers made clear that, even with a doctrinal pivot to defense, the gap between what was needed and what could be supplied was vast. The Reich's industrial system simply could not close it. Operation Overlord, depended on one condition above all: total Allied control of the skies. Every invasion plan, every timetable, assumed that bomber streams would pound German defenses, cut rail lines, and keep panzer divisions bottled up far from Normandy. But if the Luftwaffe had made the Channel coast a no-fly zone, if swarms of Me-262s and rocket interceptors tore into bomber formations with impunity, the calculus would have changed overnight. War game estimates from Allied planners showed that if bomber losses doubled to even 8 or 10% per mission, daylight raids would grind to a halt. The 8th Air Force, already stretched by heavy casualties, could not sustain that level of attrition for long. With air cover gone or crippled, the landing beaches would have become killing grounds. The risk matrix for amphibious assault shifted dramatically under these conditions. Without bombers to suppress artillery and troop concentrations, German defenders could mass fire on the beaches. Panzer reserves, freed from the threat of air attack, would maneuver in daylight, striking at the vulnerable flanks of the invasion force. Even the Royal Navy, which provided crucial gunfire support, would face new danger from rocket-armed aircraft and fast jet bombers. Intelligence summaries from the period warned that a failed air campaign would force a delay of months, perhaps into 1945, buying the Reich precious time to reinforce the Atlantic Wall and regroup its shattered armies. In this scenario, the fate of Overlord no longer rested on the courage of soldiers alone, but on a technological arms race in the skies. Each day of Allied hesitation gave German engineers another chance to bring new weapons online. The domino effect was clear. Air denial threatened the entire ground campaign, setting the stage for a new escalation, one that would soon involve rockets as well as jets. Deep beneath the Harz Mountains, the Middlebrook tunnels churned out V-2 rockets in numbers that stunned Allied intelligence. By 1945, over 5,200 had been assembled in these underground lines, each missile a product of forced labor and relentless pressure from Berlin. The promise was simple. Massed rocket salvos could rain destruction on London, Antwerp, and beyond, bypassing every air defense. Yet the reality inside Middlebrook told a different story. Sabotage became a silent resistance. Sand poured into turbo pumps, wires hidden in concrete, sugar mixed with fuel tanks. Survivor accounts and post-war inspections revealed that as many as 1 in 5 early V-2s failed due to deliberate sabotage or rushed workmanship. Guidance remained a persistent weakness. Even at peak production, the average V-2 could miss its target by several kilometers. Records from 1944 show that a typical salvo, no matter how large, rarely struck with precision. The psychological effect, however, was out of proportion to the physical damage. Rockets arrived without warning, faster than sound, turning city streets into scenes of panic and confusion. Each successful launch forced Allied planners to divert resources to civil defense and countermeasures, stretching supply lines and morale. The logistical strain was immense. Every V-2 required tons of liquid oxygen and alcohol, both in short supply. Transporting these volatile missiles to mobile launch sites exposed convoys to Allied air attacks and further sabotage. Even so, the doctrine of salvo fire, the hope that quantity could compensate for inaccuracy, remained central to the German rocket strategy. The ambition was clear: overwhelm defenses, paralyze cities, and open a window for even more audacious strikes soon to come. Johann Sanger's Silbervogel concept looked like something from science fiction, an aircraft designed to launch from a rocket-powered sled, skip along the edge of space, and glide across the Atlantic to strike the American mainland. On paper, its range and speed promised a new era of warfare. one where a single pilot could deliver a payload to New York or Washington without warning. But beneath the bold lines of the design, the technical hurdles were immense. NACA engineers, reviewing captured plans after the war, found that the heat shield required for atmospheric re-entry would have consumed so much weight that the bomber's payload shrank to a fraction of its intended size. The alloys needed to survive repeated skipping through the upper atmosphere simply didn't exist in wartime Germany. Every trade-off between bomb load and thermal protection, between speed and survivability, pushed the Silbervogel further into the realm of theory. Even more traditional America bomber projects, like the Messerschmitt Me-264 or Junkers Ju 390, ran aground on the same shoals. Engines that overheated or failed on long flights, airframes that couldn't reliably cross the ocean, and a fuel supply already stretched to the breaking point. The idea of a terror raid on the United States captured the imagination of Nazi planners, but the reality never left the drawing board. Still, the psychological effect of even a rumored intercontinental strike was enough to prompt Allied intelligence to take the threat seriously. For a regime desperate to project power beyond Europe, the promise of the Silbervogel lingered as both a warning and a mirage, a vision of global reach built on the limits of steel and science. In the race for atomic power, Germany's nuclear ambitions ran into a wall of technical and industrial barriers. The program's hopes rested on heavy water from the Norsk hydro plant at Vemork in Norway, where Allied commandos struck in February 1943, destroying key infrastructure and setting back German research by more than a year. Even before the sabotage, the German atomic project was plagued by divided leadership and chronic shortages of uranium and graphite, slowing every step from reactor design to enrichment. Interrogations of Kurt Diebner and Werner Heisenberg after the war revealed that, by late 1944, the most optimistic projections placed a working fission bomb years away, no sooner than 1947, even without Allied interference. Yet the idea of a radiological weapon, a so-called dirty bomb, haunted Allied intelligence and German planners alike. Unlike a true atomic device, a dirty bomb required no chain reaction, only radioactive waste and a conventional explosive. German scientists calculated that waste from their stalled reactor experiments could be packed into a V2 warhead or conventional bomb, contaminating a port or city center. Technical papers from late 1944 discussed this possibility, but material shortages and the risk of Allied retaliation kept the concept in the realm of contingency planning, not active deployment. The bottleneck was always industrial. Without steady heavy water production, and with uranium stocks scattered or sabotaged, even the limited goal of a dirty bomb remained out of reach. The terror lay in the potential, not the reality. A weapon more effective as a threat than as a battlefield tool. As the war dragged on, Germany's atomic gamble became another chapter in the story of promises that technology alone could not keep. In the closing phase of the war, German engineers pressed ahead with designs that blurred the line between science fiction and battlefield reality. The Horten Ho 229, a jet-powered flying wing, underwent test flights that revealed an unusual radar profile. Decades later, replica testing confirmed its shape could reduce radar cross-section by nearly half compared to conventional fighters of the era, especially against the long wavelength sets guarding Britain's coast. Yet the effect was subtle, not a cloak of invisibility. Detection range might shrink, but not disappear. Only a handful of prototypes ever left the ground, and none reached squadron service. Surface-to-air missile programs, most notably the Wasserfall, advanced through dozens of test launches. Engineers struggled with guidance systems. Radio commands and primitive radar tracking delivered mixed results, and not a single Allied aircraft fell to these weapons. Of 40 trial firings, fewer than 10 hit their targets, and production never scaled beyond isolated batteries. Technical reports from Peenemünde and Thuringia describe persistent engine failures and premature detonations, while Allied bombing raids on facilities forced repeated relocations. Inside Berlin, these technological gambits became bargaining chips. Propaganda broadcasts hinted at unstoppable new weapons, hoping to sow doubt among Allied leaders and publics. Diplomatic cables from Stockholm and Switzerland carried vague threats of retaliation, promises of terror raids and secret arms aimed at prying open a path to negotiation. But the Allies, armed with intelligence intercepts and hard-won experience, saw through the bluster. No demonstration of stealth or missile prowess ever forced a ceasefire. The final barrier was not invention, but the will and capacity to turn prototypes into leverage. By 1945, over 5,200 V-2 rockets had been produced, and more than 1,300 Mi-262 jets left the factories. Yet, operational records show that only a fraction ever saw sustained combat. Archival reports confirm that Germany's fuel output dropped by over 90% after Allied bombing intensified in 1943, crippling both production and pilot training. Documents reveal that sabotage, technical bottlenecks, and leadership disputes undermined every major wonder weapon program. Despite test flights of the Horten Ho 229 and plans for intercontinental bombers, no prototype reached full operational status. The full details of some projects, like radiological payload trials and guidance systems, remain classified or incomplete. Expert consensus holds that advanced technology alone could not offset broken logistics and failed coordination. Today, military historians point to Nazi Germany's experience as evidence that innovation without strategy cannot win wars. The surviving records make one fact clear: new weapons alone did not decide the outcome. Systems, resources, and leadership did.